Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. Assalamu alaikum, everyone. Today we will solve recitation problem for chapter 17. So let's begin. This problem we already solved it in class, so I won't solve it again. The solution is given here. This problem is extremely important and we already solved it in class. The solution is given here. This problem as well, we solved it already in class, so have a look at it, inshallah. Now let's solve this problem. So here we have a stationary train passenger who hears a frequency of 500 Hertz as the train approaches a bell on a track side safety gate. So the passenger is comfortably sitting in the train, so he is stationary with respect to the train. But of course, the train is moving at constant speed. We'll come back to that. After the train passes a gate, the passenger hears a new frequency, which is 420 Hertz for the bell sound. What is the speed of the train? So overall, the passenger is sitting inside the train, which is moving at constant speed, Vd. Okay, Vd is constant here. Okay. So on the ground, you have a bell, and this bell is emitting a sound wave. Of course, the frequency of that sound is F. This is a real frequency, the true frequency of the sound wave. Now, the frequency heard by the passenger depends on the speed of the train. So here, I will hear a frequency F1, which is 500 Hertz. And here I will hear a frequency F2, which is 420 Hertz. So here I'm getting closer to the sound. So the apparent frequency, this is the apparent frequency F prime, which is F1. So this is case number 1, and this is case number 2. Case number 1, I'm getting closer to the sound. Of course, the frequency will go in higher pitch. Basically, I will have here higher and higher frequency. If I'm going away, in the case number 2, the frequency is decreasing. So F1, which is 500, is equal to, I apply the formula for Doppler effect, is equal to F V Vd V Vs. By the way, Vs is 0 because the sound source is stationary. The bell is stationary. So forget about Vs here. Now here I will put a plus or minus. What do you think? I'll be putting a plus, of course, okay, because I'm getting close to it. Okay, so this is my first equation. Now second equation here, F2, which is, the F prime, of course, is F V Vd V Vs. Vs is 0, forget about it. Now here I will have a minus, of course. Okay, great. So my first equation is 500 is equal to F. What is V? Speed of sound, 434. It's here. I mean 343. 343 meters per second. Plus Vd divided by V, which is 343. This is equation number 1. Equation number 2 here gives me 420. Which is just equal to F 343 minus Vd divided by 343. So I have two equations, two unknowns. Okay. My unknowns are F and Vd. And I have two equations, I can solve it. Here I want Vd, let me get rid of F. If I want to get rid of F, I'll just say equation number 1 divided by equation number 2. So I will have 500 divided by 420. The F will simplify, the denominator will simplify, and I will just have 343 plus Vd divided by minus Vd. And I solve for Vd. If you solve for Vd, you will get 29.8 meters per second. Okay. So this is the constant speed of the train. Is it clear? Okay. So the solution is given here. Okay, so you can have a look at it. Next. So the displacement of a sound wave in a material, okay? So this is a material. I will not tell you which material. We will find out that this material is what? I give you the displacement wave, it's here. So S at any xn time is Sm, so this is Sm. Of course, it's in meter. This is your K, and this is your omega, okay? Where S are in meters and T in seconds. Write down the equation of pressure variation wave. So you know that if I have S at any position and time, which is S max cosine Kx minus omega T, the pressure variation wave at any position and at any time is just maximum pressure variation sine, same K, same omega. They are in quadrature. Basically, they are out of phase by pi/2. So here I have a cosine and here I have a sine. So the pressure variation wave will be this, okay? I have to get this. I know already K and I already know omega. How do I get delta PM? I apply the formula. The pressure variation amplitude is the displacement amplitude times rho times V times omega. Now, what is rho of the material? I have to give you the rho of the material. I have to give you the density of the material. And I have to give you omega. Omega, I already know. What is omega? This is omega. So I already know omega. Now, what is V? Well, we know that V is omega divided by K. So I know the omega and I divide by K and I get this V, 1,500 meters per second. So you know that the material is not air. So the speed of sound in air is 343 meters per second. This is the speed of sound in water. So here I should not give you the density of air because it's not air. I have to give you the density of water, which is this. Okay, so I guess this was a mistake. When my friend Dr. Mackey gives this, yeah, it was a mistake, but it's water. So he gives you the density of water. So you use the density of water. Instead of having this, you put 1,000. You put the speed of sound in water, you put omega, and you put Sm max, and you get this. It is your delta PM, your pressure variation amplitude. And then you write everything. Now you know delta PM, you know K, you know omega. Is it clear? Okay, great. This is just for more warm-up. Next. This is the same, okay? I give you here the pressure variation wave. I ask you to find the pressure amplitude, the frequency, the wavelength, and the speed of the wave. You just apply. Okay? You know everything. Now, let me tell you something. If I ask you to find me for this wave, for instance, this wave, if I ask you to find me the intensity of the wave, of course, you know that intensity is a half rho V omega square Sm square. So I will give you rho. I will give you the density. Let's say, for instance, in the previous example, so the density will be the density of water. The speed is the speed of sound in water, this speed here. Omega, of course, omega is this. It's given. Sm square, Sm you will get it from here. Okay? But you know that Sm is just delta Pm divided by rho V omega. Okay? So if I give you this formula here, I can ask you to find me the intensity. You can calculate everything. Okay? I will give you, of course, the density. You can calculate V, which is just omega divided by K. You can get omega. Omega is given. Sm square is given via delta Pm. Do you get my point? Okay. You know delta PM, which is delta PM is this. This is a pressure variation amplitude. You just divide by the density, divided by the speed, divided by omega, you get SM. So you can plug it in. If I want to be a little bit more, let's say, tricky, I'll not ask you the amplitude. I'll just ask you the sound level. So you have to use beta, which is 10 decibel log of this intensity divided by 10 to the power minus 12. Okay. So you know this intensity, you plug it here, and then you get me the sound level in decibel. Okay. If you move forward, you will see other problems that are solving exactly this way. Okay, now let's look at here. We have a sound wave and a detector. They are moving with the same speed along a straight line. In which situation will there be a maximum frequency shift due to the Doppler effect? Of course, you know that you have the maximum frequency shift when the source and detector are moving toward each other. So remember, you have how many cases? Let's say this is a source, this is a detector. The source is producing the sound wave. Let's say, for instance, the detector is moving away and the source is moving towards the detector. So of course, this is the real frequency, F. The frequency heard by the detector is F prime. So you know that F prime will be F VVD VVS. So let's fix the source, for instance, and the detector is moving away. So here it will be what? A minus. Now let's fix the detector and the source is moving towards the detector. So here you will have what? So he wants to increase. So of course you will have a minus. Great. Now, what about now if I have my source and my detector like this? Now the source is moving away and the detector is moving toward. So of course, F prime, which is the F I hear from the detector, will be F V VD V VS. Okay. So what will be VD? Of course, D wants to get close. If I fix S, D wants to get close. So here it will be a plus. He wants to increase the frequency. Now S is going away. So it will be here a plus also. Why? Because he wants to get away. He wants to decrease the frequency. Okay, now what about I have S here and D here, and they are moving away from each other. So F prime will be F VVD VVS. What do you think here? Of course, if I fix it, this guy wants to go away, so here it will be a minus. This guy wants to move away also. Okay, so it will be, of course, a plus. And by the way, this is the lowest frequency. They are moving away from each other. Last but not least, they are moving towards each other. This is moving in this direction, this one is moving in this direction. Okay, so F prime is F VVD VVS. Again, as we said in class, V is the speed of sound, VD is the speed of the detector, VS is the speed of the source. Okay, they are moving toward each other. Of course, if I fix this, this guy, he wants to increase, so here it's a plus. And of course, this guy wants to increase also. If I fix the detector, he wants to go forward, so here it will be a minus. And this is the highest frequency. And this is exactly what I'm asking you here. Okay, so A is the right answer. Okay, a stationary motion detector sends a sound wave of this frequency. I give you towards a track approaching the detector at this speed. What is the frequency of the wave reflected back to the detector? So you draw. So my detector here is stationary. VD is equal to 0. Okay. So he send a sound. So of course my detector, my motion detector, it plays the role of a source, okay, here at the beginning. Okay. Because he sends a sound and the frequency that he's sending is F, which is 4 megahertz. So it goes and the track is approaching, so the track is here. So the track here is a detector at first. The track is moving towards, of course, the source of sound, which is the motion detector here. So basically, this is V track. And I give you V track 26 meters per second. And now the question is, find the frequency of the wave reflected back to the detector. So first I have to get what is the frequency F prime received by the track. F prime will be F, V, VD, V, Vs. So here Vs is 0 because the detector, motion detector here is my source of sound. So it's stationary, so it's 0. Now here I'm approaching, so it will be plus. So I have F prime basically, which is just 4 megahertz, 343 plus V track, which is 26 divided by 343. Okay, so what is this? This is, of course, the frequency heard by the track. Okay, so this is the frequency at the track. You calculate this, you know everything here, of course. So you calculate it, you get 4.3 megahertz. Now that's still not the question. The question is to find the frequency of the wave reflected back to the detector. Okay? So now this frequency now will go. So now it's an echo basically. Okay, the detector now will echo the original sound at a frequency F prime, and that sound will come back to the detector here, motion detector. Now the motion detector now is a detector. So at the beginning, the motion detector was a source. Okay, and then that's the first phase. So the wave goes to the track, gets reflected. The motion detector now is detecting F prime prime. So F prime prime will be F prime. F double prime will be F prime. Now V, VD, V, Vs. Now you have to know the detector now is a real detector. So VD is 0 here. Do you agree with me? Because the detector is at rest. And now the source of the echo is the track. So here it's a V track. And the track is approaching. So will it be a plus or minus? Of course, it will be a minus because he wants to increase it. So F double prime will be just F prime, which is 4.3 megahertz, V 343, V 343 minus 26. And this you do it, you get 4.66 megahertz. You see? So that's how a motion detector is working. It sends a sound wave, it reaches the car, and of course, the car will reflect it, and then I detect it. So it goes start by F, and the track will hear F prime, and then he will echo at F prime. Now here at the detector, I will have F double prime. Now here the question is, what is F double prime? So you have to apply basically Doppler 2 times. Okay, great. So let me go to the next. So it's the first answer, 4.66 megahertz. So this is also a very important problem. Let's see it. We have a sound source and a track. They are approaching each other. Okay? Because they are approaching each other, this is the highest frequency, as you said. Going away from each other, this is the lowest frequency. Anyway, so I give you the speed of the sound source, 50 meters per second, and the speed of the track, 30 meters per second. Now the sound emits, I give you F. This is a true frequency, 0.15 megahertz. The question is, find the wavelength of the sound wave reflected back to the source. Okay? And I give you the speed of sound in air, this. If I don't give you the speed of sound in air, you take 343 meters per second in your formula sheet. But here I just say that it's 340 meters per second. Draw. You are in physics, draw. Okay? So what do? Of course, this is the original situation. This is my sound source moving at Vs, which is 50. Okay? And this is my track moving at this speed, V track, which is what? Vd, the detector at the beginning. So it's 30 meters per second. Okay. So I give you here the real F, the true F, 0.15 megahertz. So what will be F prime here, heard by the track? F prime will be F, V, Vd, V, Vs. Okay. So what is Vd? Because Vd is V track. V track. So will it be plus or minus? What do you think? Of course, it will be a plus. What about here? Will be plus or minus? Of course, Vs is moving towards it. So you want to increase the frequency. So it will be a minus. And you know this very well. Okay. So I know everything here. I know F, 0.15 megahertz, 340. Be careful, okay? I gave it to you here. Plus V track. What is V track? 50. V track, no, V track is 30, sorry. Be careful, okay? And here V, which is 340, minus Vs. V source is 50 now. This is 30, and this is 50. You calculate it, how much do you get? Let me check. Of course, this will be the highest, 0.241 megahertz. No, sorry. How much do I get here? I get 0.191 megahertz. Okay, great. Now this is the first situation. Now I want to find the sound wave reflected back to the source. Now, of course, F, which is here, reaches here, and the frequency is highest, 0.19 megahertz. Now, the track is still moving in the same direction, and the source is still moving in the same direction. Now the track will echo. So now I will have here F prime, and I know F prime, 0.119 megahertz. Okay. Now the track will be the source for the echo. So the track is a new source here. Okay, so be careful. And then my sound now is a detector. My sound source is a detector now. Okay. So now I want to find what is F double prime here. Okay. So this is the echo. Okay, be careful, echo. As we already talked about in class, in the backed echolocation. You remember that? Okay. So if F double prime will be F prime, now V, Vd, V, Vs. Now what is Vd? Is a V of the detector. So V of the detector. Now the source is a detector, so it's 50 here. So don't forget it. Okay. Now, will it be plus or minus? What do you think? Of course, the detector is moving forward, so it will be a plus. So here it will be a minus. Now, V source now is a V of the track, so which is 30. Okay. So F double prime, which is a wavelength, which is the frequency of the wave reflected, is 0.19, 343 plus 50, divided by 343 minus 30. And if you do that, you get 0.24 megahertz. Okay. So this is the frequency of the wave reflected back to the source. Okay. Okay. So the original frequency was 0.15. The track in this condition will hear 0.19, and then he will reflect it back to the source, who will now become a detector, and now the source will hear a frequency of 0.24 megahertz. Now, I want to get the wavelength. The speed of sound is just lambda f, but I want the wavelength reflected back. I know the frequency reflected back, so I can know what is the wavelength reflected back. So the wavelength reflected back, lambda double prime, is just speed of sound divided by f double prime. And if you do that, you get 1.41 millimeters, which is 0. Of course, you will get it in meters, and then you have to convert it in centimeters. Okay. So same problem as before. The echo. Great. Let me erase this and then I summarize. So this is what we did. Okay, this is the frequency detected. This is the frequency of the sound, original sound. This is the frequency detected by what? By the track. And then it's reflected. Okay. Now the frequency detected by the source, I will have to apply it again, apply basically the Doppler formula again. Great. Okay, I will skip this problem because we already solved this type of problem. Okay. So two cars are approaching each other, and I give you the frequency. So I give you two cars that are approaching each other at the same speed. One of the driver just, sounds the horn of his car, and I give you the frequency. Frequency is this, 500 hertz. The other driver will hear a higher pitch, 520 hertz, because they are approaching each other. This is the highest frequency. And then I'm asking you, what is the speed of the cars? They have the same speed, right? Yes. So you apply your formula. F prime is F V plus VD divided by V minus VS. I know that there are this sign because I know that this is the highest frequency. They are approaching each other. Okay. So I know everything. I know F prime. This is detected by you. This is emitted by me, the frequency emitted by me. This is the speed of sound. This is the speed of sound. This is the speed of the detector, which is the speed of the source because they are moving at the same speed. I have one equation, one unknown, and I solve it and I get the speed of the car. The cars, okay? They have the same car. So V S is equal to VD is equal to VC, and I get it. Okay, this is a very interesting problem, and you can do a lot of things with it. Okay? Great. So what is this problem about? We have a block with a speaker fixed to it. It is connected to a spring, and it's oscillating on a frictionless surface as shown. Okay? So this block has a speaker, and it's having a simple harmonic motion, back and forth, back and forth. The speaker emits sound wave at a frequency 400 hertz. This is a true frequency, right? F is 440 hertz. If the maximum speed of the block during oscillation is 20 meters per second, so Vmax is 20 meters per second, find the minimum frequency recorded by the observer who is here. So you are standing here, you are the detector, and of course you are static, you are stationary. So you know that F prime is F, V, Vd, V, Vs. Now, of course, you are stationary, so this is 0. Forget about it. That's why here I put 0. Now, maximum speed will happen when? Of course, when I'm at 0. Because you know that this is moving from minus x max to plus x max. So maximum speed will happen here at 0 when x is equal to 0. But will it be at 0 moving to the right or at 0 moving to the left? What do you think? Of course, if I want maximum frequency, it has to move in which direction? What do you think? To the right or to the left? Let's say minimum frequency. Okay. Let's say minimum frequency. Minimum frequency will be when he is moving away. Okay. So this gives you minimum frequency. Okay. When V of your source is moving away, okay, this gives you minimum frequency. So here I will have a plus. Okay. So let's put it. And then of course you will have your answer. I know everything. This is the original frequency. This is the speed of sound plus 0. Detector is at rest. This is the speed of sound plus 20. Plus because it's moving away. Okay. And this is the minimum frequency. And it happened when I'm crossing the equilibrium position, but moving away, basically going in this direction to the left. Now, if I wanted to ask this problem, I will not say this. I will say, oh, okay. Find the maximum frequency recorded. Of course, the maximum frequency will be F prime, will be F V plus 0 divided by V minus Vs. Why minus? Because the maximum frequency will be when the speaker will be crossing the equilibrium position, but moving towards the detector. Okay. So this will happen at x0 and Vx positive, meaning maximum and positive. Okay. You get my point? Okay. So this is Vmax, Fmax. Okay. This is Fmin, and this is Fmax. Okay. So you can calculate Fmax. Fmax will give you 467 hertz. But the question here is Fmin. Fmin just gives you 416 hertz. Now, needless to say that at x, which is plus or minus x max, the sound source is at rest. Because Vs is 0. So that means what? F prime will be F. Okay, so when the sound source is here or here, he is at rest. So this guy here, you sitting or standing here, you will hear the same frequency as the frequency of the source. Otherwise, you will be having Doppler effect. Okay. So this is how we ask problems in an exam. I will come and I will change things. Okay. So always when you solve a problem, ask yourself this simple question: when, where, how, why, where. Okay. Great. Okay. Now let's stop from Doppler effect and go to sound wave resonances. So let's solve this problem here. What do we have? Let's read it carefully. So we have a well with vertical sides and water at the bottom. Okay. So basically I have a pipe. So this is my well. I have water here. And of course this is open. So I have a pipe. This looks like a pipe with one closed end, the bottom, where I have water, and one open end. So this well resonates at 9 Hertz. If you talk, I guess you did that experiment maybe, if you went, you talk, you will hear the echo. Okay? So it resonates. But here, it resonates at 9 Hertz here. We have a standing wave at 9 Hertz. And at no low frequency. So this is the fundamental. I'm telling you that the fundamental is equal to 9 Hertz. And the question is very simple. Find the depth of the well if you know that the speed of sound is 343. So a pipe with one open end and one closed end. So you have to know that, okay? So here I have just one open end, it's here, and one closed end, it's here. So you know that the resonance wavelength are just 4L divided by N, but N has to be odd. 1, 3, 5, 7, etc. And the resonant frequencies Fn are NV divided by 4L, because this N here is odd. So again, the fundamental is just 1V divided by 4L. And this is equal to 9 Hertz. So I know V, so I can get what is L. Okay, so L is 9.53 meters. This is the length of the, or the depth of the well, Basically, this is what we, this is L. This is the height, the depth of the well. Okay. Very simple, okay? Just have to be careful. Next question. Let me just erase this. So I give you pipe A with both ends open, and I give you the fundamental, F1. Okay, I have one pipe, two open ends. So you know that the resonance wavelength are just 2L divided by N. The resonance frequencies are NV divided by 2L. But here N is any integer. Okay? 1, 2, 3, 4, etc., etc. Before, here, of course, as I said, N is odd. The even integers are forbidden if I have one open and one closed end. But if both open or both closed, these are the conditions, and we already talked about it. So, of course, F1 here, which is 480, is just 1 V divided by 2L. And then I have a pipe B. The third harmonic of pipe B is one open end. So B now, so this is for A. Of course, B, Fn is NV divided by 4L. And N has to be what? Odd. 1, 3, 5, etc., etc. So third harmonic here means F3. 3V divided by 4LB. So here, this is the length of A. Okay. So I'm telling you that F3 has the same frequency as the second harmonic of pipe A. So I'm telling you that F3B is equal to F2A. What is F2A? It will be just 2 times V divided by what? 2LA. Okay. Great. Which is just 2 times V divided by 2LA is just F1. Basically, this F1A, okay, which is 480. So I know everything. I know that 2 times 480 is 3 times V, which is 343 divided by 2 4 LB, sorry, divided by 4 LB. So this is what I have to solve. And I get my LB. Okay. Is it clear? Excellent. So you solve it. Okay, so here I want you to solve this. The solution is straightforward. Okay, so just solve as much as you can. This was a quiz given by my dear friend. So let's solve this problem here. A tube is open at both ends with air inside oscillating the fourth harmonic. How many displacement nodes are located within the tube? So tube, open end. You know that lambda n is equal to what? 2L divided by n. And Fn is Nv divided by 2L. So here I'm telling you that fourth harmonic, so n is equal to 4. Okay. Now, how many displacement nodes are located within the tube? How many nodes do we have within the tube? We discussed this already. Okay. So, to open end, it looks like this. The simplest is this. Let me erase this and put. So if you remember, I already told you that n, which is the number of nodes, which is the number of loops, okay, is what here? I have 2 open ends. So this is the simplest. This is n is equal to 1. Here I have 1 node. How many antinodes do I have here? 2 antinodes, so AA. This is 1 node. Okay. If I have 2, you can draw it, but we discussed that already. Okay. If I have a tube with 2 open ends, n, which is the harmonic number, is equal to the number of nodes. It's equal to the number of antinodes minus 1. Okay. And here I have 2 open ends. Okay. So here's the number of displacement node is equal to 4. And the number of antinode is equal to what? Antinode is equal to 5. Yeah, etc., etc. If I had a tube with 2 closed ends, now n will be the number of antinode, which is the number of node minus 1. Yeah. So be careful with that. Of course, if I have 1 closed end and 1 open end, n is odd first, that's number 1. N is equal to the number of node, which is equal to the number of antinode. If you go to the complement slide that I gave you, you can find this and you can figure it out by drawing the harmonics. Anyway, you can solve this also. So we have a pipe which is closed at one end, meaning open in another end, and I give you the length of the pipe. And I tell you that the third harmonic standing wave is set in the pipe. At what distance from the closed end is the first displacement node? Displacement antinode. Great. So you can draw if you want. But let's just exploit the data of the problem. One pipe, one closed end, one open end. So you know that the resonance frequencies looks like this. And n should be odd. Okay, great. So I gave you the length. So you know the length, you know the speed here. V is 343 meters per second, length is 1.2. So you can calculate your basically F3, okay? So this is your F3, and you can calculate your lambda 3, okay? This is lambda 3. Great. So once I get my lambda 3, now let me come to the question. At what distance from the closed end is the first anti-node? Because the closed end will have a node, the first anti-node will be here. The distance between them is lambda divided by 4. The distance between a node and an anti-node in any case is lambda divided by 4. So I know here it will be lambda 3 divided by 4, and I just calculated it. Is it clear? Okay, great. So here I gave you L, 1.2 meters. Another way, okay? N, which is 3. So I know that it's one open and one closed end. Okay. So basically I know that lambda n is just 4L divided by n, but here n is equal to 3. So I know lambda 3. Lambda 3 is just 4 times L 1.2 divided by 3. Okay, and this gives you 1.6 meters. So once I get lambda 3, I know that the distance between node and anti-node is lambda 3 divided by 4. This gives me 0.4 meters. Okay, as asked here. There are many ways, okay, but all the ways lead to Makkah. Okay, some students, they don't want to use this formula. They will use a speed formula. Basically, they will get the frequency, F3, as we did here. And they will say, oh, the speed is lambda 3, F3. And then they get lambda 3, etc., etc. You know this very well. Okay, now let's go to sound level and intensity. So a source emits a sound with equal frequency in all directions. So this is what we call an isotropic source of sound. So if the displacement amplitude is triple, what is the sound level increase? Okay. I'm looking for delta. Okay. So how can we solve this problem? So look at the intensity relation with sound level. What is the relationship between intensity and sound level? Okay, let's continue. I stopped it by mistake. So let's read the question carefully and then we solve it. So a source emits a sound with equal intensity in all directions. As I told you, this is a definition of isotropic sound source. Okay, it emits equal intensity in all directions. So if the displacement amplitude is triple, what is the increase in the sound level? So let me just do this. Okay, so intensity, as you know, is linked to the displacement amplitude, is half rho v omega square sm square, right? Okay, it's in your formula sheet and you know it by heart now. So this is intensity number 1. I take sm number 1. Now intensity number 2 is just half rho v omega square sm2 square. But I told you that the displacement amplitude is triple. So sm2 is equal to sm1 3 times. So that means basically I2, it will be just I1 9 times. Okay. So I just take this SM2 and I plug it here, but with a square, I'll have 9 times. Okay, so this is a fundamental thing. I2, if I triple the displacement amplitude, I multiply by 9 the intensity. Now, what about the sound level? So beta 2 will be what? Let's calculate beta 2. It's 10 times decibel log of I2 divided by 10 to the power minus 12, which is I0. Okay. And beta 1 will be 10 decibel log of I1 divided by I0, which is 10 to the power minus 12. If I want the increase, I just take beta 2 minus beta 1. So let's calculate beta 2 minus beta 1. You know the properties of the log, right? So it will be 10 dB log of I2 minus, of course, log of I0. And also here you will have minus 10 decibel log of I1 minus log of I0. You see that the I0, of course, will simplify. Okay. So I'll just have what? 10 decibel log of I2 minus log of I1, which just gives you log of I2 divided by I1. You remember? Yeah, these are the log properties. So basically you'll have 10 decibel log of 9, because I2 divided by I1 is equal to 9. Okay? And you calculate it and you get this answer. Okay? The increase is just 9.54 decibel. Okay? Is it clear? Okay, great. Next. I solve this very interesting problem, but we already solved it by the way. The pressure in a traveling sound wave is given by this equation. So here I'm giving you the pressure variation wave as a function of position x and time. So this is delta P max, pressure variation amplitude. This is K, and of course this is omega. Now the question is, find the level of sound, the sound level of the wave, and I give you the intensity, and I give you the density of air. Okay? So you know that beta, which is the sound level, is half rho v omega square sm square. So I give you rho, this is rho of air. V, how do we get it? Of course, it will be this divided by this. Yeah? And it will be roughly 343. Okay? You know omega. Omega is this. So V is omega divided by K. And you know omega, this is omega. Sm, well, you know that it's delta Pm divided by rho V omega. Okay? Sorry, this is intensity, not sound level. Okay, this is intensity. Of course, if I want sound level, I just say beta is 10 decibel log of this intensity here divided by 10 to the power minus 12. Okay, so this is exactly what we will do. So this is the sound level by definition, and you know that this is the intensity by definition, and you know that this, if I know delta Pm, I know Sm. Okay. So I just rewrite my intensity as a function of delta Pm. Okay. So this is what I have, and I plug it in my, and then I get my answer. Okay. Is it clear? Okay, great. So the speed here we took, of course, 343, but if you want to make it properly, what do? We just say that, the speed is omega divided by k, which is 315 divided by 0.9. If you calculate that, you will get something like that. 315 divided by 0.9. So the speed is 350. 350. So textually here, we don't need to use this. We just need to use this. Okay. We need to use this meters per second. Is it clear? Okay, great. Next. If it's not clear, do it again because this is very important. Thank you. Okay. Now, let's solve this problem here. We have a sound meter placed 3 meters. It's a sound detector basically, placed 3 meters from a point source. And it measures a sound level of 70 decibel. So if the power of the source is reduced by a factor 20, what will be the reading of the sound? So beta, which is the sound level, is 10 decibel log of the intensity. Now what is the intensity? Is power of the source divided by 4 pi r square divided by I naught, which is 10 to the power minus 12. Okay, this is the intensity of a source of sound. You remember that? Okay, great. Okay, and sometimes also this intensity is just half rho v omega square sm square. Okay, so you have to know how to navigate between these things. Now beta 1, which is 70 decibel, is 10 log of the intensity, basically the power of the source, divided by 4 pi r1 square. By the way, r1 here is 3 meters, okay? Divided by I naught. This is beta 1. Now the new reading, which is beta 2, that I don't know, but I can calculate it easily. That's what I want to calculate. Will be 10 log. Now the power source now has been divided by 20. The distance is the same, r1 square, I naught is the same. Okay. So the question is, what is beta 2? So let's get beta 2. Of course, beta 2 is 10 log of what? PS divided by 4 pi r1 square divided by I naught. By the way, this is 70 decibel. I'm just separating this to this. Basically, I'm just saying that, log of PS divided by 20 is just log of PS minus log of 20. Okay. So I just put this here out. So I will have what? Minus 10 log of 10 log of 20 basically. So do you see what I did? Okay, it's just math actually. Okay, it's not difficult. Math is easy. So I'm just using this log of this. So I'm separating this, okay, between this and this 20 here. Let me put it explicitly. So basically I have 70 minus 10 log of 20. And this will give you this answer. Okay. So beta 2 is 10 log of PS divided by 20 divided by 4 pi r1 square divided by I naught. Okay. So you agree that this is 10 log of PS divided by 4 pi I1 square divided by I naught minus 10 log of 20, just by using this. Okay? Anyway, so straightforward. Now let's go to the next question here, which is very important. And I wanted to give you this as a quiz. So yes, okay, we have a sound wave. It's emitted at this frequency with this sound level. If the air density is this, find the displacement amplitude. So I give you frequency. So I'm giving you omega, which is just 2 pi f. Okay. And I give you the sound level beta. Now I'm giving you also the density of air, 1.22 kilogram per meter cube. I'm asking you SM. Can you do it? Okay. The answer is this. So I think you can do it, right? Of course, beta is half rho omega square. Don't forget, sorry, intensity. This is intensity. It's half rho V omega square SM square. Okay. This is the intensity. Intensity is half rho V omega square SM square. So I know rho. I know V. I know omega. I want SM square if I know I. Well, how do I get I? Well, you know that beta is 10 log of I divided by I naught. So that means I, which is the intensity, is I naught 10 to the power beta divided by 10. Divided by 10, yes. Yeah. So here my I will be 10 to the power minus 12 watt per meter square, 10 to the power beta, which is 100, divided by 10, 100. So basically my I is just 10 to the power minus 2. So I know everything. So this is 10 to the power minus 2. So my SM will be the square root of 2 times 10 to the power minus 2 divided by rho 1.22 divided by V, which is 343 divided by omega square, which is 2 pi 250 squares. And then you calculate. Right. Now let's go to interferences. So in this example, for instance, needless to say that if you take the speed that we calculate here, you will get this. Okay. If you take the speed, which is 3.43, you will get this. This is the right answer. Okay. We already solved this. Now let's talk about this. So interferences. So what do we have here? We have a sound wave, a sound with a wavelength of 40 centimeters. It travels in the right from a source through the tube that consists of a straight portion and a half circle as shown. So here we have my source here. Okay. The sound, this is my detector here. So when I arrive here, half of it will go through this, half of it will go through the arc, or a portion will go through the arc, and a portion will pass through the straight tube. Okay. So a portion will pass here and a portion will pass here. As we said here, part of the sound travels through the half arc and then interfere with the rest of the wave, which is going in the straight direction. So the question is, what is the smallest radius R that results in an intensity minimum at the detector? Okay. So as you know, minimum intensity means wave number 1, which is going in the straight direction, and wave number 2, which is going in this direction, they will have to destructively interfere. So destructive interference. What does it mean? Of course, it means that delta L divided by lambda should be equal to what? Half, 3 halves, 5 halves, etc., etc. So basically, delta L has to be half lambda. Do you agree with that? Yes. Okay. So this is the smallest. So I want the smallest radius. So of course I will take the smallest half integer. Now, what is delta L here? What is the path length difference? Well, the path length difference is just L2 minus L1. L2 is just half of this. It is basically this semicircle here. What is a semicircle? What is the length of a semicircle? The length of a full circle is 2 pi r. So the length of the semicircle L2 is just pi r. And what is L1? L1 is just 2 times r. So L2 minus L1 is equal to pi r minus 2r, and this has to be half of wavelength. That means r have to be half wavelength divided by pi minus 2. You calculate, and of course you will get 0.175 meters, which is A is the right answer. Okay. Now I can play with that. Okay, you know what I want to do. Okay, I can play with this. Great. I can play with the frequency because this lambda is G divided by F. I can play with telling you, oh, maximum intensity at the detector. What is, you know, what will give me the second largest radius, second smallest radius, etc., etc. Okay, but you know the idea. It's very simple. Okay, now let's solve this problem here. Let me remove this. So we have a point source, and I give you the power of the point source. This is PS, 30 watt. So it emits isotropically. A small microphone intercepts the sound in an area, and I give you the area of the microphone. Calculate the power intercepted by the microphone, placed perpendicular to the radial direction and 200 meters away from the source sound. Okay. So you know that the intensity at any distance r is the power of a source of sound, which is, let's say, a point source, which emits isotropically, divided by 4 pi r squared. 4 pi r squared is the area of the sphere at radius r. Okay, so I can calculate the intensity. It will be 30 watt divided by this, because here I'm at an r which is 200 meters. So I can calculate it easily, and I get it. And this is the intensity. Now that intensity is the intensity for the whole area of the sphere of radius r. Now what is the intensity? Okay, what is now the power intercepted by the microphone? Okay. So of course, this intensity is also, yes, it's equal to the power intercepted by the microphone divided by the area of the microphone. Okay, so this is what I have to use. So power intercepted will be area, and the area is given, which this is the area, times PS divided by 4 pi r squared. Okay? So this is the power that I intercept. Okay? The intensity is the same, but the power that I intercept is proportional to the area of the detector. Okay? And we discuss this. This is just because of conservation of energy. Okay? Great. And we discuss this intensively in class. So be careful with this type of problems. Okay? They are a little bit simple, but you can be easily misled. Great. Now let's solve this problem here. It's also an easy problem, but let's just go through it. So a loudspeaker produced at X is here. Sound wave, and I give you the frequency of sound wave, 170 Hertz, 71 Hertz. The sound wave enters the tube and the sound energy is divided equally before traveling along the fixed and movable tube. Okay, great. Initially, the distance d1 is equal to d2. You see, d1 here is equal to d2. Then the movable tube is slowly pulled out. This is a movable tube here. This is a fixed tube, and this is a movable tube. You see, it can slide here. Okay. So it's gradually and slowly pulled out. You see, it's moving in this direction. You see, this d2 is bigger than now than d1. The question is find d2 minus d1 for which the microphone at y, so here I put a mic, detect minimum sound intensity. Okay. So at the beginning they are equal, d1 is equal to d2. Of course, they will positively interfere here, constructively interfere here, and I will hear maximum sound. But I don't want that to happen. That's why I'm moving this movable tube. Now I'm asking you, what is d2 minus d1 such that the intensity that I detect here at the output will be minimum? So how to do that? Of course, for minimum interference, I need to find a path length difference, delta L, divided by lambda, which is just half. This is the first one. Basically, delta L is just lambda divided by 2. This is what I'm saying here. Okay. So delta L has to be lambda divided by 2. Okay. Right. Now, what is delta L? The path length difference. This guy here will go in this direction. This is the first length, and this guy will go in this direction. This is the second length, L2. This is L1. So path length difference is L1 minus L2. Of course, they will share this. So this will cancel in L1 minus L2. Now you will see that the path length difference is just basically, this distance and this distance 2 times. But you have here this distance 2 times. So the path length difference, delta L, is 2 times d2 minus 2 times d1. So the path length difference, delta L, is 2 times d2 minus d1. Okay? Because this is the same for both of them. Okay? And this delta L has to be half lambda. That means d2 minus d1 has to be a quarter of lambda, which is a quarter of what is lambda? Well, lambda is v, which is the speed of sound, 343, divided by the frequency, which is 171. And I get here 0.5 meters. Okay, and A is the right answer. Okay, so be careful. Sometimes in the solution there are some typos. For instance, here there was a typo. Okay, it happens. We want you to detect these typos. Right. Okay, so these 2 problems also are not very difficult. I want you to solve this one. Okay, this first one. And the second one, the second one is a little bit more interesting. Look at the second one. We have 2 identical sound sources, S1 and S2, that are placed along the vertical line, as shown in figure 1. Okay, they are placed here. So they are connected to the same oscillators. Okay, so they emit sound waves that are identical and in phase. When only speaker 1 is on, the intensity found at O is I. If you switch both speakers on, what is the new intensity found at O? Okay. The intensity of 1 at O is I. Intensity of 2 at O, if O is only what is, if 2 is only working, it's I. So what is the new intensity? If I put both of them together. Okay. So some of you will say 2I, basically I1 plus I2. No, because they will constructively interfere. Okay. You will have a constructive interference. Okay. So the sound wave that is emitted here will constructively interfere with the sound wave. Why? Because delta L is 0. Okay. This is basically constructive interference. So they will constructively interfere. Okay. So the new intensity will be 4 times I, not 2 times. Okay. So do you know why? Yeah, because they will constructively interfere. So you will have 4 times I. Do you want me to demonstrate it or it's clear? Well, you know that, of course, intensity is half rho v omega square sm square. So here I1 will be sm1. I2 also will be also half rho v omega square sm2 square. Sm1 is equal to sm2. So intensity 1 is equal to intensity 2 is equal to the intensity. Okay. But when both of them are together, I will have a resultant intensity. Okay. At point O, the intensity which is resultant, which is coming from both, will be half rho v omega square. Now the resultant amplitude square. So the resultant amplitude will be 2 times Sm cosine phi divided by 2. Square, of course. This is the resultant amplitude. Do you remember that the resultant S, which is S1 plus S2, I went through this in class, is 2 times Sm cosine phi divided by 2 cosine k L1 minus omega t phi divided by 2. If you remember this, and this is the Sm prime. So this I'm using this here. Now, of course, if they are constructively interfering, this phi is 0 or multiple of 2 pi. So my intensity resultant is just half rho v omega square 2 times Sm square. Basically, I have 4 times I. Yeah? Because of constructive interference. Okay? Be careful, it's not 2 times. So be careful, it's not this, it's A. In order to demonstrate it, you know, you just use this. Okay, let me stop here. You have, you know, you can practice. The rest is straightforward, but they are very important. Solve them in order to have a feeling of the different type of problems that we ask. If you solve this, you are not only good for the exam, but you are good for the quizzes, you are good for the final exam, you are good for the midterm exam, okay? So I wish you the best. Assalamu alaikum wa rahmatullah.